Good morning, everyone. This is Dan Tanning from the Institute for Catastrophic Loss Reduction. Thanks very much for joining us this morning for our September Friday Forum. Today, we're very happy to have John Englander, who is an oceanographer consultant, leading expert on sea level rise. He's been working in this field for the past 30 years, and he served as the CEO for the Cousteau Society and the International SeaKeepers Society, and he was recently appointed executive director of the new International Sea Level Institute, which will start operations this year. As we all know, sea level rise is a big issue for Canada and our coastal communities in Atlantic Canada and BC. So we know that this is a big issue here, and today Mr. Englander will provide a good global perspective. We understand that he's just in from Greenland and is going to have some good information on us from the global perspective. So we're looking forward to a very good presentation. And I just wanted to remind you before we start that our next presentation will be October 14th. Originally it was planned for September 16th next week, but it was moved to October 14th. And that will be Francis Weers, who will talk about climate modeling and extreme rainfall risk in Canada. So with that, I'll pass it to John Englander.
Thanks, Dan. It's a pleasure to be here. This meeting came out of a meeting Paul Kovacs and I had in Calgary at the Pacific Northwest Economic Regional Conference. And he said if I was in Toronto, I should stop by. And I happen to be here. So this hopefully is an overview. And if it meshes with you as an organization or your individual company's perceptions, hopefully it's really just a launching point for what we can do in the future. The title, obviously, Rising Sea Level is not a flooding event, is a little bit perhaps challenging, but it's not an event in the normal sense that it's something that can happen on a date and a place and then recede. Okay, it's different than an event, and that's really the case I want to make to you, but show you how it's a different form of flooding that amplifies the other flooding risks. And it's something that we really can't do based upon history, which is a problem for the insurance industry. To say in one sentence my premise here, and this is actually a sentence I wrote early this morning for you, as I tried to say, how do I frame this for this audience? It's a stealth flooding risk that's hidden in worse routine king tides, extreme high tides that is, and storm events, and will get worse for decades, regardless of efforts to slow the warming. And that's a provocative statement, because most people either hope that the efforts to reduce greenhouse gases, which are very good, and we'll talk about that, and the Paris Accord that was recently signed by the U.S. and China and others, that's not going to stop sea level rise. So we need to think of, but it is part of changing weather patterns. And all of this is a problem and a challenge for the insurance industry and for catastrophic loss. So this is very timely. You probably are aware that temperatures are changing. This is the third year in a row of record ever high temperatures since 1880 when we had a global temperature record. This is the third year in a row that it's the warmest year ever. And as this NASA chart shows, the temperatures aren't uniformly distributed. And in fact, up here in the Canadian North or the high Arctic, around the pole, it's warmer than average. It's about double the global warming average. And that's problematic both for Canada as a country, but also for the melting of the polar ice cap. The warmer world means several things. It means weird weather. Weather's breaking out of patterns. Weather's always weird in terms of you can't predict it for sure, but it means that the patterns are going to change. That's why I call it even weirder, okay? It's a technical term. But it means that because of excess heat and moisture in the air, that the ocean atmospheric currents are breaking out of patterns that have existed for the last 10,000 years, the period that in geologic time we call the Holocene. It's been a fairly stable period for climate. Not day-to-day weather, but the climate's been pretty stable for 10,000 years. Kiss that goodbye. It's done. That's a profound concept. We've put more heat in the system. The currents of the oceans and atmosphere are changing, the jet stream, etc. It's not going to go back to normal. Can't. And I'll make that case. Ice sheets and glaciers on Greenland and Antarctica must continue to melt, raising global sea level, directly changing shorelines on coastal areas through marshlands and far up tidal rivers. Contrary to what most people assume, that this is like a storm that hits on the coast, it will hit Hartford, Connecticut, insurance capital of the United States, and Sacramento, California, which are 100 miles inland because they're on tidal rivers, as is London, Paris, Washington, D.C., and a lot of other places. So this is what we always think of. And another effect is that we'll get more rain, more snow, and unpredictable storms. Those are all direct consequences of a warming planet. Sea level has changed over 400,000 years, up and down in a pretty regular pattern of, do you use feet or meters here more? What meters? Meters? Okay. So I'll tell you what the meters are. It's going to say things in feet because most of these slides are for U.S. audiences. Excuse me. They're metric challenges, you know. But 120 meters is what sea level goes up and down about every 100,000 years. It's the ice age cycle, we call it. We've all heard of that. The last ice age peak was about 20,000 years ago. From the right-hand side there, it's the low spot, and sea level rose about 120 meters, or about 390 feet. Bridging to what most people jump to and say, well, if we just get climate under control, like the Paris Accord, the 196 nations agreed in December, of course. Canada, U.S., and China were all part of it, and the U.S. and China just signed, and that's great, and it's good that they tried to set a goal on warming, but here's the problem. This thermometer gives you a really simple netting it out. The best calculations by a group called Climate Interactive, based at MIT, Massachusetts Institute of Technology, certainly reputable, that, and this model has been used by all sorts of agencies all over the world now to really simplistically translate the goals and the policies into temperatures for this century. If we do nothing, business as usual shown in yellow. We could be as much as 8.1 degrees Fahrenheit or 4.5 degrees Celsius warmer. That's a disaster. The goal is in green, to keep it to 2 degrees Celsius over pre-industrial. We've already warmed about 0.9 degrees Celsius, so that would allow another degree of warming over the current, right? The problem is that that's a problem by itself. It means that even if we reach the goal, it's double the warming we've already had. Most people miss that. But the bigger problem is that the proposals that are on the table between now and the year 2030 to get us toward the goal only get us to 3.5 degrees. These are their own numbers. They're not John Englander's numbers. So should we be pursuing the Paris Accords? Absolutely. If we don't, the warming will go to the 4.5 degrees. But we need to strive harder. But even if we reach the goal, we're going to get more warming than we already have. We're not going to get the toothpaste back in the tube. Last Saturday, front page of the New York Times, or actually their feature on their web version, you may have seen it, of flooding of coasts caused by global warming has already begun. It's forget theoretical, it's happening. And they profiled cities down the east coast of the United States that are getting more nuisance flooding, sunny day flood events during king tides, etc. Right? The Arctic's melting. You know that. Certainly close to on Canada's doorstep on the northern border. Even though it's happening, I'm going to take you to Greenland in a minute from a trip. I was in Greenland 2 weeks ago today. I'll show you that. But I always like to start with the biggest misunderstanding for most audiences, and maybe some of you don't feel ashamed, is to think that the melting Arctic is why sea level is rising. There's no effect. Run the experiment at home. Take a glass, ice water, cubes float about 10% above, just like the icebergs. Draw the line. If you just let the ice cubes melt, it won't change the level of liquid in the glass. You have to add an ice cube or add melt water. Okay? It's the only way to get the level to rise. Again, it's counterintuitive for most people. They assume that that's why it's happening. Oh, sorry. Let me back up here. The two valuable lessons, though, from this that you can just see from what's happening in the Arctic is that as you go from bright white to dark ocean, it's like taking a white roofed house and painting it black or dark blue. you know what's going to happen to the temperatures in the house, right? They're going to go up because dark absorbs and white reflects. That's happening to the planet. But the second lesson that's valuable is that the Arctic's been frozen for about 3 million years. It's going to be ice-free in our lifetime for increasing numbers of days. That's an incredibly powerful statement. So when people say, oh, well, climate's changed before, well, they're right. It has. It's changed in the ice age cycles. Before the 4 million years of the ice age cycles, it changed differently. But let's put things into real perspective here. The Arctic's been frozen for 3 million years. As I say in my book, and it's an absolute true statement, if you had said to any geologist in 1950, year I was born, could the Arctic be ice-free in this century? That's, no, do the math. And there's just, no, you can't possibly melt that ice in a century. We're doing it. It's reality. There's a number of types of flooding. You know, and when flooding occurs, you probably don't care where it came from. If you're up to your arse in water, you know, or knees or whatever, or chest or nose, the fact is you need to get rid of the water, right, or recover or get out of the way. But there's different kinds of flooding, and we really got to start to break that down because, and Canada's a good example, you now have some flood insurance policies. You didn't used to have flood insurance. It was, so policies got invoked under backing up sewer lines and things like that, which is maybe a rainfall flooding event, right? But we're all learning and we're trying to cope with this changing time, which is different than the past. So I would like to suggest to you that there's 5 or 6 kinds of flooding. There's storms which are coastal impact. There's runoff events or downstream flooding that can happen in a place like Calgary, thousands of meters above sea level, or 1,000 meters above sea level, right? Okay, as you had, and we'll look at. Extreme tides, which are a cyclical, predictable pattern according to an 18.6-year tide cycle that we can predict exactly to the inch or centimeter to the location years in advance. Been known for 1,000 years. Okay, we think of it as king tides. And then, I hope it doesn't contrast too well there, but rising sea level and subsidence of land, those both are a different kind of flooding. Because, so if the land goes down or the sea goes up, and you have to add them to get the net effect on any location, we'll talk about that. But those are permanent. They're not going to reverse for thousands of years. And then erosion, people confuse that, but that's a little bit different too. So that's a different color here. This is just an image to remind us of what a severe storm flooding does on a coast. This was Hurricane Sandy 4 years ago. This is Calgary. Again, flooding, but totally different cause. Heavy rainfall, not storm, not coastal, not sea level. Hong Kong, bad event. San Francisco, every 28 days, the Embarcadero goes underwater. It's not even on the ocean. It's in the inside of San Francisco Bay, right? Most of you have probably been there at one time or another. Well, it's 7.5 miles of waterfront. The elevation was established 140 years ago with some very good engineering. They would have built it higher if this was going to happen every 28 days. Didn't happen until about 2 decades ago. Something's changing. Neighborhoods where storm drains are put in to take water back up with salt water now. That could be Fort Lauderdale or it could be Delta, BC. It doesn't matter. The different kinds of flooding have different drivers, causes, predictability, magnitudes, permanence, and impact areas. If we're going to insure against that, we need to understand that, right? Your own industry, the Geneva Association, any of you familiar with this report? Paul, it's worth looking at. 2013. If you send me, I'm going to tell you how to get a hold of me, and I'll send you the link to it if you want. There's 4 findings in this 3-year-old study. One is that we're in a new normal, quasi-irreversible for a number of hazards. I'm going to actually detail this in a second. The traditional methods increasingly fail to predict. This is your own industry out of Geneva's 90 members. This isn't me saying this. That the extreme event prediction is ambiguous now. And the 4th of their conclusion is that climate change and ocean warming threaten insurability of catastrophe or risk generally. That's a powerful statement. Let me give you their own words, actually, from their executive summary. You can read them yourself. Number one, there's new robust evidence that the global oceans have warmed significantly. Ocean is the key driver of extreme events. Ocean warming has effectively caused a shift towards a new normal for a number of insurance-relevant hazards. This shift is quasi-irreversible. Even if greenhouse gas reductions completely stop tomorrow, oceanic temperatures will continue to rise. Two, in a non-stationary changing environment, that means caused by ocean warming, traditional approaches solely based on analyzing historical data increasingly fail to estimate today's hazard probabilities. A paradigm shift from historic to predictive risk assessment method is necessary. Three, due to limits of predictability and scientific understanding of extreme events in a non-stationary environment, changing environment, today's likelihood of extreme events is ambiguous. As a consequence, scenario-based approaches and tail risk modeling become an essential part of enterprise risk management. And four, in some high-risk areas, ocean warming and climate change threaten the insurability of catastrophic risk more generally. To avoid market failures, the coupling of risk transfer and risk mitigation becomes essential. Doesn't get any stronger than that, does it? What's happened with sea level rise? In the last 150 years, since we've had decent records, the tide gauges, et cetera, it's been going up. Well, this one's in millimeters. We've had about 18 to 20 centimeters of sea level rise in the last century or so. And the line bubbles up and down, but not only is it a clear upward trend, but the trend is accelerating. And the red line in the upper right there is from satellite data. Since 1992, we've had satellites adequate with radar altimetry to be able to better resolve or with greater precision value of sea level changes amid the waves and tides and everything else.
Why is the graph on the left there on the right, you have negative numbers?
Oh, that's just relative to a reference year. That's just, it's the point. It's just, yeah, they're just, whatever the reference year was, and I think it was in the 90s, okay. It was from the reference year when they first started the satellite data. Oh. It's just up or down, but it's a continuum. You should add the numbers together to net it out. Okay. Sea level, again, 390 feet, 120 meters since the last ice age. Two good takeaways from this. One, besides the amount, it got to the present level about 6,000 years ago, which is pretty much our human civilization. It didn't rise smoothly because of the way the ice sheets will collapse. We're at the early stage of that now. It's not going to rise smoothly in the future. We know 14,000 years ago it didn't. This all happened because of the ice ages. And if you saw the scientific movie Part 2, the Ice Age Meltdown, kids or grandkids, you probably watched this. And there's 3 kilometers of ice in the background there, about 5,000 meters. And as that melted, we got 120 meters of sea level rise. Works out. And that's about all the science you need to know about this. Okay, the scientists make this a little too confusing sometimes. To put it in really graphic terms, in the building environment, the risk environment, the catastrophic loss environment, we're at the present level at the 30th floor. 20,000 years ago, sea level was at the ground floor. 390 feet down, 120 meters. When all the remaining ice on the planet melts, hopefully not too soon, sea level will be another 17 floors higher. That's the amount of ice remaining on the planet, another 65 meters. It's not a problem, right? Who cares? I guess we'd be underwater here too, wouldn't we? Right? We're on the second floor. By the way, you can get. I'm not going to give you all these slides as a for you, but I will give you about a dozen of them that you can use. The graphics, particularly, which you're free to use, and I encourage you to use them. If you'll send me an email, take out your smartphones or iPads, whatever, ICLR at johnenglander.net, and you'll get download instructions for about 2 megabytes of slides, so you may not want to do it on your phone. And that's my Twitter and Facebook and LinkedIn stuff. My book's available on Amazon and is an ebook, a Kindle book too, for those that like that. So the same sea level rise that we just looked at of 18 to 20 centimeters, here's not Canadian cities, but 13 U.S. cities. This is a graph done by the Union of Concerned Scientists. And it shows that the red line, the red warbly line toward the bottom is global average sea level rise, about 18 to 20 centimeters. We'll have to approximate feet, but just at a relative scale, you can see visually that from Grand Isle, Louisiana, which is near New Orleans, we had 46 inches. I don't know what that translates to into meters, but probably about 0.5 meters or something like that. Meter 1.3 meters. 46 inches. And going down from Virginia Beach, Boston, Miami in the middle, and Los Angeles at the bottom, and 4 inches, which would be about 8 centimeters, or 10 centimeters, something like that, 10 centimeters on the right. And that's because California is uplifting because the Pacific plate is going underneath California, so why you get all the earthquakes out there, the plate tectonics. So land can subside like it does in New Orleans or Venice or Virginia Beach, Norfolk, different places, or it can uplift like Los Angeles or even worse in Alaska. And most of Canada is uplifting because of the retreat of the ice happening later here. Make sense? Okay, so land, I'll tell you, goes up or down. And you have to add or subtract that from sea level to get how sea level appears locally. So sea level is not a global number. The problem is, for sea level rise, the ice that's on Greenland and Antarctica. That's 98% of the potential sea level rises in those two places. All the other glaciers from Alaska to the Alps of Europe and Peru, etc., are small stuff. The other thing that's surprising for most people is to realize that the Arctic Ocean around the North Pole, your north, you probably know this is not land, it's frozen ocean, and again, like the ice cubes in the glass, has no effect on the level of the ocean. Most people don't understand that. But it's the ice on land that, like adding ice cubes, and we'll look at that. The other factor that I don't even think I mentioned in here that's small but relevant is that as the oceans warm, just by themselves, liquids slightly expand. It's called thermal expansion. And about half of the rise we've had in the last century is from thermal expansion of seawater. That's going to be, that'll continue, but the melting of Greenland is going to overtake that very quickly. In fact, it probably already has done so. So another point of confusion is to say, oh, it's mostly the, the thermal stuff. It was, but that's all changing now. Again, I'm going to take you to Greenland just a moment for most people's orientation. To remember that the North Pole is in the middle of that sea ice, and it is melting, not in the way most people think. The interesting point, though, is as the Arctic is melting, the red line showing you from 1900 our best recreation of how the square area, the square kilometers of sea ice is declined. What's interesting is in the background there is 12 different models. That's those light-colored and various colored lines. The melting has happened faster than all the models. Look at the angle of the red line compared to everything else in that graph. Okay, the models are inadequate. Well, some would say, well, they don't know. It's true. The models are not right. But any thought that the models are exaggerating? I'm going to show you a few places that we can prove that the models are underestimating.
Sorry, just to clarify, those are the severe scenarios, RCP 8.5 or?
No, we'll get to that in a minute. This is how the Arctic sea ice was predicted to decline in square kilometers, okay, on the left, and how it has actually happened, okay. These are various models from, this is from Britain, Hartford is up here, I know. The U.S. model is, there may be a Canadian model. It's different parts of the global climate model that we're modeling how the Arctic sea ice would change because of the importance of, you're not only losing the reflectance of that bright white ice to the dark ocean, as we talked about earlier. The other big effect of the melting Arctic is the ice was a barrier to thermal transfer from heat energy in the ocean to the atmosphere. And as that disappears, that's the reason the weather patterns are changing. Because there's a lot of heat in seawater, and even though ice is 0 degrees Celsius, it was still a thermal barrier. Right? And so there's a feedback loop as the Arctic melts. So the problem for sea level, just zeroing in that, is as we have glaciers on land, as they enter the water, it's like adding ice cubes. Or the glaciers slide into the sea would have the same effect on a bigger scale. Or the meltwater from the land. All of those things add to sea level. Interesting to note that the glacier here shown is not white. I mean, there's part of it's white on the left, but on the right it's dark. And the darkness that I'll show you in Greenland 2 weeks ago is, it's from two different reasons. One reason we've been concerned about is soot and other black carbon that comes out of the atmosphere from all the industrial uses and coal plants and burning cow dung in India and stoves and every, all the different ways that we get particulate matter up in the atmosphere that will swirl around and tends to come down heavily in the Arctic. So that darkens the snow. But there's a new phenomenon happening in Greenland that I hadn't really paid attention to until 2 weeks ago. I'll show you in just a minute here. So this is from Greenland 2 weeks ago. I went with the senator and the head of the Coast Guard. In fact, that's Admiral Zukampf, Commandant of the U.S. Coast Guard. We were there literally 2 weeks ago today. And, whoops, there we go. You all know about icebergs being 10% above the surface. This is to remind us, it's hard to judge the shape of it underwater. From a shipping standpoint, that's a concern. That's Admiral Zukampf looking at over Jakobshavn Glacier. I'm going to show you a few different images of the Jakobshavn. It's really significant for a few reasons. So the glacier is broken off and into the fjord, which is what he's looking at there. And you can see how much ground is exposed. And that gravel, or actually the dirt that he's standing on, is a really fine dirt that I hadn't thought about a whole lot. But glaciers, that island's been covered for hundreds of thousands of years. And as the ice grinds away, it grinds the rock and it pulverizes it, gravel and then dust. And what's happening is the dust is now blowing, as the glaciers recede, the dust is blowing onto the glaciers and turning them dark gray. That's almost as bad as the black in terms of heating, speeding up the heat, the melting. One of the reasons that was so poignant was that as we speak, the crystal serenity, you may be aware, is traveling through the Arctic because the Arctic seaways are opening. And even there's reports the increasingly ice-free Arctic was in the news last week. Well, there's a terrible fallacy, and we were standing there on Jakobshavn Glacier, which is where the glacier spawned the iceberg that sank the Titanic in 1912. And the fact that the opening of the seaways makes people think, oh, well, we'll go see the Arctic, not realize that's an invitation for disaster. There's more icebergs than ever. It's not ice-free yet. Increasingly, it's about 30% covered in ice. And so icebergs that's an iceberg in the slurry. In the far upper left, you can see the face of the glacier, actually. Everything in our view is a slurry of water in the fjord. That's an iceberg in the middle there that's floating down to the ocean 8 miles away, 12 kilometers, okay? That's going to get out in the shipping lanes one day. That's a concern to the U.S. Coast Guard and the Danish Coast Guard, or Joint Arctic Command. Here's a good visual. These photos were all taken by the Coast Guard's official photographer who was with us, which was great. So here you see the glacier. You can kind of see it's declining. You can start to see the blackening as you wind up with land in the foreground there, but the darkening gray on top of the ice. That's a 15-day-old photograph. This is what's called a moulin in the lower right there. This is where the meltwater kind of gathers together in streamlets and finds a weak spot and then bores a tunnel down. And the problem is that the meltwater not only gets down below and will work its way to the ocean, but it's getting underneath the ice, lifting the ice off the bedrock, so the glaciers are no longer working on bedrock, grinding away. They're now floating, and so they're doubling, tripling, quadrupling their speed of movement. And then when they reach the edge, they calve into icebergs. So it's an obvious physical mechanism that's no doubt happening, and that's the biggest moulin we've ever seen, frankly. There's about 1,000 of those, so who knows. But that's what's, again, part of the real-time photos. And so that's the calving face of Jakobshavn. That's one of the calving faces of Jakobshavn there. That's where the icebergs are breaking off the glacier, which comes from the ice sheet farther back. The ice sheet covers 80% of the island, and there's about 100 glaciers, which are these meandering, slow-moving rivers of ice that drain the ice sheet, the one ice sheet on Greenland, and take it to the ocean, and now you've got the mechanism that it eventually does raise sea level. Is that clear? Okay. So here's an overview, a satellite image of that same glacier. The same face we just saw is up here where it says 2013, or is actually the red line for 14. This is Jakobshavn Glacier from a satellite view of what we just were looking at, and it's showing how the front of the glacier has receded since 1875. Actually, 1851 is the first line. And what's really amazing when you think, and because the Greenland people have kept track of this. I mean, they've lived there for forever. I mean, for 10,000 years. The Inuit. So from 1851 to 2000 is here. From 2000 to 2015 is here. In 10 years, it's done what it took 100 years to do. This isn't opinions. This is not ambiguous. This is the biggest glacier in the Northern Hemisphere that daily puts out as much water as New York City uses in a year, that spawned the iceberg that sank the Titanic, that's churning out icebergs faster than ever, and of concern to the Coast Guard, which is why we're there. Pretty simple visual evidence. And most people are confused. Oh, let's go to the Arctic. It's opening up. It's safe. You know, it's fun. We'll see how global warming's allowing us to see places we've never seen before. Sorry, I guess I didn't include. I had some advances in there. So there we are. 2000. That's what I was explaining. That's actually the next glacier north, but it allows you to kind of, again, visually see the, you know, that's the face where it calves off or spawns icebergs, and then farther back. There's a helicopter down there in the light. See that? Just for scale. I mean, this is, you know, 200 meters tall. The Greenland ice sheet. This is the ice mass, not square area. This is the volumetric, which we get from satellite data going back about 10 years, showing how it's declined. I mean, the trend is pretty clear. You talk about betting the trend, you know, I mean, pretty good bet right there, right? There's no evidence whatsoever that that's changing. It's pretty straight line. We think it's going to increase, but the slope, but even if it stayed that level, we've got a problem, because that does add to sea level. So what are the projections for sea level rise? Some of us were talking about that earlier. I'm going to explain to you why it's very problematic. We know that historically, during the stable climate of the last 10,000 years, sea level hadn't changed much. And then in the last 2 centuries of the industrial era, as we've been warming the planet just slightly, but increasingly, that warming has increased, melting has increased, and sea levels increased, but modestly. But now we're entering a new phase. And the projections aren't very good, and they won't be very good. And it's really important, as that Geneva Association report alluded to understand why they're not going to be very good. And it requires a different kind of approach in terms of assurability. Antarctic is the big problem. It's 7 times the amount of ice, as you've already heard, than Greenland. It has the equivalent of 56 meters of sea level rise in it, whereas Greenland has 7 locked up in it. Now, again, those aren't going to happen this century or next century. Let's be realistic here, but it does put in perspective that we're in a new era of geologic history. As the ocean rises, the shoreline moves inland, but it's counterintuitive how it does so. The ratio is about 300 to 1 as a global average. Totally illogical until you start to think about the inland incursion isn't happening at the beach. It's happening up the rivers and through the marshland and in flat areas from Florida to Bangladesh to Vietnam that are very different shoreline configurations than the Maritimes or British Columbia here, right? In fact, if we plot 1 meter of sea level rise in 10 different places here, the red just shows you the relative amount that would just simply disappear purely by sea level rise, so just as a map exercise. So from Vietnam, we get a lot. The Amazon Delta, we get a lot. Louisiana, New Orleans, we get a lot. The Netherlands, huge. Yukon a bit, and so on, but different relative amounts. So it's the elevation of the land, in effect, the profile, topographic profile. In the United States, well, globally, the biggest reference that a couple hundred nations subscribe to is the Intergovernmental Panel on Climate Change report, IPCC. It comes out every 5 or 6 years. It's a really good piece of work. I don't want to be understood to be dissing it, but unfortunately, it's well known in the scientific community that it really falls short in predicting, or in the way it explains sea level rise as a top-line number that people take away. I'm going to show you that quite specifically. The problem is the 10 to 32 inches, which is up to 92 centimeters in metric of sea level rise, basically excludes Antarctica, which is a problem because it's 90% of the potential. It doesn't include the two things that it can't quantify well is what it's doing, and they're kind of footnotes them, and we need to understand that footnote. The U.S., the latest report, well, actually, there's one more recent than this, but in 2012, this was the U.S.'s contribution to that IPCC report, and it's telling what they said and most people missed. The takeaway sentence about sea level from this report, done by NOAA, U.S. Geologic Survey, Department of Defense, CERTA, and Army Corps of Engineers, is we have very high confidence, a greater than 9 in 10 chance, that sea level will be between 0.2 meters and 2 meters. Now, there's two problems with that. One is the range. I mean, is it equally possible? But would you be able to sell an insurance policy with a greater than 9 in 10 chance that something would happen without knowing what the other 10% was? No. Nobody buy it, right? That's like Russian roulette, pretty much. And in fact, if we look back at the IPCC's own recommendations from 1990 for sea level and just to the present year, and in 2002 they revised their projections and kind of narrowing and elevating projections for sea level rise in centimeters here. And now we can look back and say, how well did they do? Well, not very well. The gold line is sea level and the red is a smoothed out trend line. The truth is, even in the last 2 decades and the last decade, the IPCC's methodology was low by their own numbers. Why? Are they trying to lowball it? Are they trying to say it's good? No. It has to do with a protocol that was set in 1988, and it's logical in a way, but it's terribly deceiving, as I'm going to show you. Future storms. We'll come back to the IPCC in a minute, but the problem is the atmosphere is 0.9 degrees warmer. There's 4% more water vapor in it, and 90% of the new excess heat that we've trapped in the atmosphere has been stored in the ocean. It's like a thermal battery. It's like a hot rock. I mean, it's not going to go anywhere. The heat's there. By the laws of thermodynamics, you can move heat around, and it takes energy to move heat around, but you can't, once it's in the system, it's going to stay here. We don't cool anything. A refrigerator moves the heat to the kitchen, and the air conditioner moves the heat from the house outside, but we can feel the heat when it gets there. You can feel that excess heat, and it takes energy to do those movements, right? That's the flaw with saying, well, let's cool the oceans or let's cool the Arctic, which is by scale impossible, but or impractical, but there'd be no place to put the heat in the Earth system in the void of space. So when we take that first chart of sea level that I showed you, the blue line over 400,000 years, and we put on top of it global average temperature for 400,000 years and carbon dioxide measured in parts per million, an amazing picture takes shape. And this will be one of the slides you can get if you just send me that email. And I encourage you to use it. I did this chart for my book. It's in black and white in the book, and it came from some work by Dr. James Hansen, probably one of the most foremost climate scientists, and his colleague, Cousteau. And they actually helped me do this for the book. They'd never quite assembled it this way before, and it's a really telling picture. I think there's more information about climate change in this one graph than anything else possible, because it shows there's 4 ice age cycles. This is actually going on for 4 million years, not the 400,000 years. So this is like the last 10% of what the graphs, when they've been keeping this pattern. But it's interesting. So is there a regular pattern? Yeah, it's between 95 and 125,000 years. It's called the Milankovitch cycle. Without getting into it today, it's just a page in my book. It's It's the tilt, wobble, and shape of the ellipse of the Earth around the sun. It's like a giant summer and winter. That's what the ice ages are. Okay. We don't think of it that way. We're at the warm spot. 20,000 years ago, we're at a cold spot. There was more ice on land. When there's more ice on land, sea level's down, right? Temperature and CO2 go together. Either one can proceed. They're locked in by simple physics, again, beyond the scope of what we're going to do today. But you can see a pretty clear pattern there. The peaks line up. They're pretty evenly spaced, right? And the problem is what's in the upper right, in the red ellipse. That carbon dioxide is broken out of the range for millions of years of 180 to 280 parts per million. It's now at 400 parts per million. The other two lines are trying to chase it now. We just don't know how quickly that happens. It's never happened in human civilization. The last time sea level got higher was 120,000 years ago when it got 7 meters higher than today. We're going to blow past that. We just don't know when. We know that data from ice cores from Greenland and Antarctica. There's 20 different teams now doing drill core studies when the air bubbles that are locked in the slivers of ice that come out of those ice cores, the air bubbles are pressurized. We know they're intact because when you drop them in water, they hiss actually. I mean, they've been intact for 140,000 years here and 800,000 years in Antarctica. And the analysis of that shows us the percentage of carbon dioxide. And we know temperature because there's 2 molecules of oxygen, 16 and 18, and by molecular weight, they vary with temperature. So we have a conveniently locked in thermometer and carbon dioxide percentage sample going back 800,000 years now. That's relatively new science, only been around for about 20 years. Kind of like drilling a tree ring and getting data, you know, from horizontally, but this is vertical, of course. And what's really great is that the correlations between Greenland and Antarctica, even though the Greenland data set is shorter, 140,000 years, I think, to Antarctica is 800,000. They correlate for the 140, so we know it's a global phenomenon. So that the percentage of the carbon dioxide and the temperature variations reflect global trends. Close enough. The problem for sea level is Antarctica, ultimately. Right now it's Greenland, but Greenland's just the first stage. But it's advanced from Antarctica. But the big problem is Antarctica. There's 6 glaciers we call the Pine Island glaciers that are showing ominous signs of movement. And I'm going to show you some more detail of that in a minute. Last week there was also, when I was in Greenland, so 2 weeks ago, 3 weeks ago, there was an announcement that a big part of Larsen B broke off, a line's forming that will calve off an area of ice shelf the size of the state of Delaware. I don't know if that'd be in Canada terms, but big. Hundreds of kilometers, and Antarctica is confusing. This has been colorized to show movement and warming. How are we doing on time? We okay?
Yeah, quarter to.
Okay, we'll be fine here. East Antarctica is growing a little bit, and it has to do with more moisture getting in the air and coming down as snow. The problem is, so West Antarctica is unstable. It's got these glaciers I'm going to show you in a moment, which are sliding toward the ocean and destabilizing in a way. And when they slide, they will way overwhelm the ice gain on East Antarctica is the problem. The ice shelves here and then the peninsula are kind of the 4 areas of Antarctica that maybe to just try and keep separate. It's confusing because it's all white. It kind of blends together. But this helps to kind of distinguish. And there is a lot of confusion. People say, well, John, how come Greenland's melting but Antarctica's growing? Well, it's only East Antarctica that's growing, and we know why. It's more moisture in the air. It's coming down as snow, just like you get more rainfall the rest of the planet, as with a warming ocean, which is exactly what we predict. That an oblique aerial view of those same Pine Island glaciers here, where the blue arrow is in the 7 o'clock position. Whoops, sorry. This is the problem. Those 6 glaciers, the Pine Island Glacier, the Thwaites, etc., hold 10 feet of sea level rise just in those 6 glaciers. By the way, Jakobshavn that I showed you earlier in Greenland holds 1.5 feet of 50 centimeters of sea level rise, metric, okay, globally. When it slides into the ocean or melts completely, it will be another 50 centimeters roughly globally as an average. These 6 are 6 times greater. And they are moving and we're monitoring them, but we don't know how and when they're going to slide in the sea. And that's why we can't say how fast sea level rise past maybe the next 20 years when we don't really expect anything catastrophic. But we need to begin anticipating a new era ahead, because this is as simple as gravity. There is no conceivable way to stop these babies. I mean, they're so huge. And I get emails from people saying, oh, well, why don't we just freeze the Arctic, or why don't we refrigerate the oceans, or why don't we, I mean, it's silly. But some people say, well, build a wall to stop the glaciers of Greenland. I mean, I with the commandant in the center of it, say, it's as big as Young Street. Okay. I mean, it's forever, and it's 2 miles. It's 2,000 meters of ice. You could build any structure you want. It's like rock. It's just gonna ignore it. I mean, it doesn't matter. A glacier will go where a glacier wants to go. It's like stopping a tornado or tsunami. People have no comprehension of what we're talking about. It's different. It's a different scale. It's a force of nature. It'd be like saying, well, let's stop the earthquakes from happening. And the problem is worse than what you'd assume, because a cross-sectional diagram here of that same glacier from Antarctica, it's undercut now 40 kilometers back. So what we see, we now know from remote operated vehicles and penetrations that again, it's destabilizing, because and we know it, we don't believe it will slide in the sea for 20 years, because by the latest data, these lips of bedrock will restrain it, basically. Okay? But after 20 years or so, nobody knows. And it depends on how much heat we put in the system, which gets back to energy policy. Are we going to use nuclear, wind, solar, coal, tar sands? All of those things affect how warm the planet gets. So to put this in IPCC perspective, and Dan, you talked about the RCPs, and the latest climate study that I showed you there puts possible climate change scenarios into 4 models, or 4 scenarios. They call them RCPs. It's a confusing term, and it goes 2.6, 4.5, 6, and 8.5. And there's a numerical equivalent to that. It's watts per meter squared, but let's just keep it simple. It's what they've decided are the 4 possible scenarios to look at for climate. So here's the shortcoming. This is my graph, but of their data on page 1180 of the IPCC book, if you want to go check it out. It's a table 13-5 from the IPCC report. You have to wonder where I get this from. But they didn't do this graph, because this graph would be far too clear for people to read. They're scientists, after all. I shouldn't take it. It's well-intentioned, but sometimes we have caught up in our own technicalities and minutiae. Okay? And we don't communicate well. And that's what I've decided my job is. So to take their numbers across the 4 possible scenarios by the last 2 decades of this century, the years 2081 to 2100, right? Here's what they're saying could happen to sea level, and from what sources across their 4 scenarios. They're saying we're going to get, and these are in inches, I'm sorry, so you have to kind of guess, but just relative scale, it's not going to matter, I don't think. Land water storage is going to contribute 2 inches. That's 5 centimeters or something like that to sea level. Across all 4 scenarios. It begins to show you that there's some problem, because if it's a phenomenon related to warming, why doesn't it change with the 4 scenarios? It's because of the uncertainties. You don't plot an uncertainty. You plot what you know will happen, but that leaves out the uncertainty. And that's their methodology problem, by the way, which you'll see in here in a second. The thermal expansion of seawater, which we talked about, that's the one that has the least lag time and is most definable, because as the oceans warm, we know how it's going to expand. That's simple physics. It's small in proportion to the 3 kilometers, no more than that. So what am I saying? The ocean depth is an average 12,000 feet, so that's 5,000 kilometers or something like that. Did I get that right? No. It's about 3 kilometers, I guess it is. Regardless, okay, the ocean slightly expands, okay? Glaciers is shown here in green. Greenland in purple, Antarctica in blue. Now notice this, just skip to Antarctica. What's the problem with this picture? They're saying against the first 3 scenarios of climate change, of if you say lowest, low, medium, high, medium, and then that it's going to get 2 inches, which is 5 centimeters of sea level rise. from Antarctica. Well, I think you probably already know enough to know that that's unlikely it's going to be that little, right? And in the worst scenario, it's going to be half that. You say, that's not possible. You can't take the most extreme scenario for warming and say, how high will sea level rise, and then break it down and look at this and say, I mean, there's no person I've ever shown this to, scientific or otherwise, says, oh, well, that makes sense. It doesn't make any sense at all. It has to do with uncertainty. You know from what you do in your probability risk or your departments in your companies that underwrite and figure out risk, we do it statistically. Standards of deviation. We want like 3 standards of deviation ideally. It's a 90-some% confidence that a number will be thus, right? Whether it's actuarial, whether it's life insurance, whether it's car accidents, whether it's fires, that's how we base insurance, right? The problem here is we don't know how much heat we're going to put in the system. We can't run the experiment in a lab and put Antarctica in a laboratory, and effects don't scale with ice. Like avalanches, you can't plot an avalanche when it's going to happen and how many cubic miles or kilometers. You just say there's a potential. It could be this to this, but it's going to be wide because the dynamics of the crystalline structure of an avalanche are such, like an earthquake. These geophysical crystalline issues of ice sheets collapsing, avalanches happening, earthquakes happening, defy good prediction. You can't model them. You can't put them in a laboratory, and the variables are so complex that you can't come up with the normal number that we want to come up with. Make sense? So what's happened is they've left out the uncertainty, but they've then totaled it up, and everybody wonders, oh, well, you know, maybe they're wrong here. Maybe it's this or this. And what I like to say is, you know, I wrote a blog post 2 weeks ago. It's on my website, The Elephants of Antarctica and Greenland. And it's saying, these are all the mice. I just collapsed the scale here. It's the same 20 inches, okay? If we just add in the 6 Pine Island glaciers that you saw 5 slides ago, and which is 3.26 meters of sea level rise that we've documented or that's in the pipeline, ready to slide into the ocean sometime in the next 50 to 150 years, that's what that would amount to. Who cares about the minutia about these? We have an elephant standing to get in the pool. But scientifically, we don't know when he's going to get in the water. So it's a footnote. So we're measuring the mice that are in the water. It's a problem. The latest U.S. government study, sorry to not do the Canadian studies, but if we move forward and turning this into a program, we can get into Canadian studies. I'd certainly invest the time in that with you, Paul. But this came out in April this year. Regional sea level scenarios for coastal risk management, U.S. government, Department of Defense, EPA, Department of Energy, NOAA, Army Corps of Engineers, and oceanographer for the Navy. And I've also got, I don't do many blog posts. You can sign up, I get like 2 or 3 a month. I mean, so it's not going to overwhelm you. But this was another blog post. It said, the latest study shows that we need to change the way we plan for things. And they have a very similar line to that Geneva study. They say we can no longer predict and then act, which is what we want to do. We want to analyze data, predict risk, and then act, right? That's what we've been trained to do. They say we can't do it anymore because of the nonlinear, sudden changes that are in the pipeline that we can now measure, and we just know are going to happen. The same thing the Geneva Association said. We need to consider extreme scenarios. So, to conclude, and I'm glad I think we're right on the schedule to take questions. Sea level is largely ignored because one, it's dwarfed by the short-term risks of storms and king tides. They're bigger and can happen next month, right? So we worry about them. We're unable to quantify how bad it will be this century for the reasons you now appreciate. Makes a real problem. We're used to predicting based upon thousands of data points. Even with earthquakes, we have thousands of data points. Paul and I were talking earlier that even in Canada, you're going to be able to predict the probability of earthquakes because we have tremors. We have all sorts of data that can be extrapolated. If you get 30 or more data points, you're in good statistical territory in terms of confidence of the numbers, right? We haven't had a collapse of these glaciers in 120,000 years. We know what happened. We just don't have enough to go and extrapolate. And we're warming hundreds of times faster than it happened in nature. The implications are simply too devastating to consider. Miami's going to be gone. Parts of the Maritimes, parts of Vancouver, Delta, BC, right? Who wants to consider that? Prince Edward Island, Sandbar, right? We don't like to look at those things. But you in the insurance industry know we have to prepare and give people ways to begin to consider. It's a daunting challenge. But as most of us know, problems create opportunities. And if there is a risk, there's a way to help people through that. We may need to be creative. Next point I've already made. We have no prior experience. The last time this happened was 120,000 years ago. Sea level's been level for about 5,000 years, all of human civilization. That's why we just can't get it through our thick skulls that it's going to change. As one of the chapters of my book, I start with a tale from Haida Gwaii, Canada. I was finishing my book in April 2012, and I was working on a project in BC, which involved Haida Gwaii, and with the old Queen Charlotte Islands, I think most of you know. And I went there, and there was a young guy, about 30 years old. He said, "What do you do?" I said, "Well, I'm an oceanographer." I was working on something there for somebody in Vancouver. And I said, "Yeah, and I'm writing a book about," and I was really trying to get this book finished. And I said, "And I'm writing this book about sea level rise." He says, "Oh, the flood." I said, "What?" And he said, "Well, you know, our oral traditions." He said, "We have the raven, the flood, and the orca, and so on. And there's a tale. They were on that island 13,000 years ago when sea level rose." I put the tale in the book. It's one of their oral traditions. They described they kept having to move higher and higher and then move to another island. That's when sea level rose 14,000 years ago. It's probably the same as the Bible flood, the biblical and the Quran. Fascinating. Mm-hmm. And then the disaster scenario for sea level rise is probably beyond 20 years, and that's beyond the normal time horizon. For most people, long-term planning today is where we're going to lunch tomorrow, right? What can we do about it? Well, as an example, this is a town in the Netherlands, Vlissingen, down by the Belgian border. And as an example, the Dutch have been dealing with sea level rise, or actually coastal risk, for 1,000 years and recovering land from the sea, as you know. And on the right is the ocean. Then you can see a levee being built up. You can count the steps, and you can see the road is built up from the levee. And you can see that big building in the center is actually on a pedestal even higher than the road height, another 2 meters probably. And by regulation in this town, the bottom floor up to 5 meters is a wash-through. No critical electrical equipment. If they do get a storm wave or an extreme tide, no damage done to the structure of the building. Smart engineering. We can do that in some places. But Miami, where we have porous limestone, that won't work because the Netherlands is like New Orleans. It has enough clay in the soils. You can build a levee and keep the water out to a degree. But that won't work in porous limestone, places like the Bahamas or the Florida Keys or the Maldives or so on, because the water just come up through the ground like Swiss cheese. But to show you one final example from the Netherlands that shows good and bad, we can design clever structures to deal with the risk of flooding. And most of you have seen this. Anybody actually been there? No? Okay. Well, this is the Rotterdam Harbor Gates called the Maasland Kering. See if you give, I think we've got time just for 2 minutes about Dutch history here. So the seminal event in Dutch history, modern times, is February 1st, 1953. That night, a storm blew up quickly in the English Channel, hit London and hit the Netherlands, collapsed the levee, and 1,835 people died that night. And so it was like a September 11th type moment for the country, but natural. And they said, we're going to engineer way past this. We got water covered. We're the water experts. So they came with this whole system, and this was the crowning jewel. About $800 million. And the gates closed, and they figured they'd close a couple times a year, and they designed them for 1 in 10,000 year storm, for the worst case of flooding from the 3 rivers that join there, the Schelde, the Meuse, and the Rhine. And then we also want to prepare for sea level rise, so they built in 30 centimeters a foot of sea level. 1 in 10,000 year storm, and 1 foot of, you now know there's a disconnect there. But they're good engineers. In 1980, when they designed this, it was fine. By 2003, they knew they had a problem. They tracked the Arctic and Greenland and Antarctic as well as anybody. And there's no way they're going to have just a meter of sea level, 30 centimeters of sea level. So they spent $800 million in the structure, and the engineers have told me, John, if we knew then what we know now, we would have built this 2 or 3 meters higher to get a better return on our investment. Because it's a perfect example. If we know up front what something could be and build the foundation accordingly, you know, we can even add floors on a building. You can start with a 1-story building and keep adding floors if the foundation anticipates a 10-story building. You can't build a 1-story building with that foundation and then add 9 more floors. The foundation won't hold, right? So you've got to design structures knowing where they're going to get a better return on investment, particularly in the face of uncertainty, and we're not doing that. Which is really ironic because we plan for the worst case earthquakes. We plan for the worst storms. We plan for the worst fire, tsunamis in Japan and elsewhere. We're not planning for the worst sea level rise. In fact, we're taking 4 possible curves, usually taking the average, and the top curve isn't the top curve. I mean, this is really lunacy. To conclude, sea level will continue to rise despite greenhouse gas reduction. That's unfortunate. It really upsets some people to find that out because they hope that if we just all go solar panels and electric cars and everything else and do all the other good environmental things that we should do. And if we don't do those things, it'll get worse. So let's be clear. But there's no way, if the world went, here's the test. If the world went 100% solar now, never burned another barrel of oil or another lump of coal, is sea level going to stop rising? No, because the heat's already been stored in the ocean. The ice has to melt. The scientific projections tend to underestimate. The 2 key components of sea level rise are glacier movement and collapse in Greenland and Antarctica, both of which are accelerating. We can see that, measure it, no doubt. We are headed back towards the situation of 120,000 years ago called the Eemian, when sea level reached 7 meters higher. We don't know when we'll get there. And I believe that planning should begin to invest recognizing sea levels and shifting shorelines, following the Dutch example that the most enlightened examples now in the Netherlands are now anticipating 3 meters of sea level rise. So I do 2 things besides giving briefings and keynotes, and this is just really an introductory of Paul's invitation. I was in Toronto at somebody else's expense. But I really do appreciate the opportunity. You're a perfect audience, and I think Canada is perfectly poised in the evolution and development of its insurance policies to really begin to embrace this and start to contrast it with the flooding in Calgary to the other kinds of flooding you're seeing or erosion in Prince Edward Island that I'm sure are of concern to your members. Briefings are helpful. So keynotes are good at conferences to get people thinking, get wider audiences. Briefings to bring it into companies and so on and say, let's drill down on this. There's some ways we do analysis that we call a 9-box matrix and looking at something came up with a strategic analysis of assets, valuable and exposed or something like that. I have to look it up. The planning is to look at multiple options to satisfy due diligence, risk analysis, and avoidance of negligence, which for a lot of companies and even law firms is becoming on the horizon. And then, begin to think about adaptation differently. Think bigger. I said to the guy, I was sponsored to go to Calgary at that meeting, Paul, by the Cement Association. And you may recall Michael McSweeney, the head of it, was saying that they knew they had some issues because they were creating greenhouse gases. They were looking at how to reduce them. They were cognizant of that. And not only did I compliment them on that, but I said, we're going to need more cement, is the truth. We're going to need to build bigger. When we're designing infrastructure, let's think bigger. Well, of course, that's good news for the cement industry, right, and construction trades. But the best example actually came 2 weeks ago in Greenland with the Admiral of the Coast Guard that you saw and the head of the Danish, the Joint Arctic Command that's there in Greenland, the all their different services are in one unit in Greenland. And after I was done with my briefing, I said, I know budgets are tight and it's hard to plan more than 10 years in advance. But here's a simple example of why you cannot keep kicking the can down the road and procrastinating. Because just as one simple example, both your organizations approve bridge heights for vessel clearance. The bridge that is designed and approved tomorrow, whether it be 50-meter clearance or a 53-meter clearance, is not going to affect the cost one bit, maybe 1%, right? You visualize that. But if in 43 years from now, the glaciers of Antarctica or Greenland let go and sea level's risen 2 meters and vessels can't get underneath the bridge, it's going to cost you a lot more than 1 or 2% to replace that bridge. So the truth is, if we force people and try and price and try and do some different kinds of risk projections than you've ever done before, for reasons you now appreciate, I think, we can get a better return on investment. We can invest in the future. But counterintuitively, this is one of the things we're delaying, and just letting somebody else deal with it is going to make it worse. And we need to think about that, because it could be in some of your careers. I mean, some of your younger, Paul and I probably won't see that era, but kids, grandkids, I mean, this is going to happen. That's what got the admiral, the head of the Coast Guard there. I gave a keynote to them at their lunch meeting for all the admirals last November. And I said to them, you have 200 bases that are vulnerable to sea level rise this century. It's not in your operating problems tomorrow. But it's time to think about how to raise those bases, relocate them, get more land, go to Congress, whatever you need to do, because it's going to be your legacy. And I made the case. I did some of these same kind of slides. And he called me a month later and he said, I get it. Let's go to Greenland and make sure we see this firsthand. I took a senator. It was a really pretty cool trip. But I think Canada has a tremendous opportunity. You're really here at ground zero. The seaways going through the Arctic are on your doorstep. I think the structure of your insurance industry, from a little bit I know, may put you in a better position because you're not responding to the National Flood Insurance Program in the United States, which has really got them in a hole. So, good point to take questions, I think. So, do we have any questions?
Sure. Yeah. So I think what we'll do, we have
here in the back room. So.
Oh yeah, for sure. We have for those online, you can submit questions using the question box. We have a few people in the room, so we'll take some questions in the room first, and that'll give you a chance to think about questions and submit them online. But yeah, we have a couple questions.
And I must say, I have to flee at 11:30. So if there are other questions, you can submit them to an email, and I'll respond, and you can distribute them. Okay.
Yeah, great presentation. To clarify one point, when you say the Dutch are anticipating a 3-meter sea level rise, is that by the year 2100?
It's by 2100, but there's actually two schools of thought. There's the official Delta Works Commission, which is now to 1.3 meters. They've raised the guidance, okay? But there's a group within the government that says they should be more cautionary and plan for higher 3 meters. And so they're kind of how quickly to implement that. It's a little bit up for debate. But there was a meeting held in 2008 by some experts where and the Queen, even though the Queen's not in that position, she said, in the face of uncertainty, let's do the responsible thing. Let's plan for 3 meters. But some people in the government don't want to.
The year 2100.
Right, 2100 for sure. And it will be worse beyond. I'm glad you brought that up because I didn't say that. The year 2100 is a deceptive number. It's 84 years from now, too far for most people to be concerned about. But it's not like the problem's going to end then. It's going to get the first decade of the next century will be even worse. And so every year we talk about 2100, we're a year closer, and we're almost saying, well, okay, that's what we're planning for. But the truth is, if you look at a bigger picture, nature doesn't care what year the century turns, right?
Just related to that question, so you mentioned the work that the Dutch are doing, and they're considering 3 meters. Is there any other governments that are increasing their estimates and designing for it, or the Dutch only?
Yeah, no, I mean, there are. I don't know that I can say, definitively that one is better than the other. In Hamburg, I don't know whether it's federal, state, or city, but there's a new area called Hafen City, which is the new harbor area, and they've designed it for a full floor of flooding. But one thing I didn't say is that sea level is a permanent rise. I mean, maybe I implied this, I guess. Storms and high tides are on top of that, but at sea level rise, it raises everything else. So we tend to respond, as I said, to the fear or threat or risk of sudden flooding next week from a storm, heavy rainfall event, which is going to get worse because we evaporate more moisture into the air, okay, or the extreme tides, or if they all pile up together, if you get a high tide event when a storm hits, okay, and a heavy rainfall altogether, it's even more. But at sea level rise, it's going to lift the whole package, okay? But we tend to design for the temporary risk, okay, if it recedes and pump the water out. What we don't think through is that sea level is a whole different character. It's only going to go up. It's a one-way street. And it's just creeping along. It's like the old kid's fable of who's going to win the race, the hare or the tortoise, you know, and the hare's jumping around. That's sea level. Okay, or that's storms, I should say. And the tortoise is sea level, just plodding along as the ice melts. So, yes.
Thank you. That was a real eye-opener. Really. You took what you did in Calgary and even built on it in so many ways, so thank you. The discussion about river flooding management and to manage disaster risk reduction has been a dialogue going for thousands of years. And it's my understanding of current best practice on the river flood management side is to move away from trying to go to each community or each local and say, look after your problem, and start to look at a basin and look at a broader area of analyzing the risk and trying to get some coordination across a bigger area. I'm trying to think of coastal. How do you manage the emissions reduction? We're trying to do a global exercise, but the adaptation to the fact that sea level is rising. If one property owner built a 7-meter barrier, the water just comes around the end and it got nowhere.
Yep.
So do you manage sea level rise community by community by community? Do you manage it province or country by country by country? Or do you have to, anyway, how do you get your head around it?
I was at the University of Miami, Florida, a School of Architecture 2 nights ago, and that question came up. And I said, you know, uniquely, sea level demands that architects, and that's what they were there for, the students and the faculty of their profession. I did this at the U.S. Naval Academy, by the way, a few months before. And same thing, and sea level demands that we think about it structure by structure, building, but also community, because architects want to make sure that this, you know, that there's social ambiance and that there's restaurants and shopping and, you know, and the government wants evacuation routes and utilities to work and all that stuff. So sea level rise, to design for it, to answer your question, we've got to think of it at 3 levels. Building by building, because that's typically what most people are involved with, this building, right, versus the next building. We've got to think of it at the neighborhood level. There's no point in being the highest building in the neighborhood if the stores and the fire department and the hospital goes underwater, right? And then we got to think of it in a larger community, whether that's city, metropolitan area, state, or nation. And it would vary depending on which area we're in, how sparse. But we have to think of it at all 3 levels, because you're exactly right. If the road gets raised, the water is going to run to your house or your restaurant, right? But we can take a page from Seattle and Sacramento and Chicago over the last century have raised elevations where they had too much flooding. I don't know if you know this, but in Seattle, if you ever go there, there's an underground tour downtown. There's 2 companies that offer it. I just did it in April when I was there. It's fascinating. In the 1800s in Seattle, the city was developing, and a lot of the fill land, they put sawdust and wood products in there as cheap fill, and it was starting to subside, you know, as happens. But they also built it too low, and they were getting more and more frequent flooding from the combination. Not sea level rise back then. And but it was a nuisance and a problem for the hotels and restaurants downtown. So when the fire of 1889 came through and wiped out 20 blocks or something like that, they said, let's get ahead of the curve. They built the streets up. They said, we're going to build the streets up 1 floor. I think about 12 feet, 4 meters, okay? And so they put ladders to get across the street from each hotel lobby and restaurant and so on, okay? And you can now still go in it. They dug them up, kind of. They were forgotten. And now you can go there, and some people have actually recreated bars, functioning bars and stuff like that. But so over a decade, they got everybody to abandon the bottom floor and build a new lobby, okay? So we could do things like that, but we're going to need to think really creatively, and this is outside of our construct. So I do want to get to the questions here. The one thing I would leave with is this scary and depressing and daunting? Absolutely. And none of you were trained to do this. I wasn't either. Okay. This is either the worst news you've ever heard or the best. Because when do we get to reinvent professions, from architecture to engineering, from insurance, law, finance? Because it's already been done. Okay, the big names are there. No. This is like exploring outer space, folks. But it's in our community. I mean, think about it. It's in your profession. Ensuring this is going to be hard stuff. But somebody's going to come up with products, right? So, daunting, yeah. Stuff to think about. Do you have enough information now to do it? No. I'd love to help you proceed. Some of you have resources of your own to do it with. That's fine. We need to help the world build higher. We need to think bigger. It's really that simple. Ice melts at 0 degrees Celsius. Doesn't care which political party you belong to. Yeah.
So just one more thing to clarify. I'm just looking at my notes, and I don't know if I wrote this down right. But if all the ice melts in Antarctica, did you say 65 meters of sea level rise?
Antarctica is 56, Greenland 7, all the glaciers of the world are another 1. So now we're up to, the total is 65.
Okay, so
all the ice in the world.
But only 3 meters by 2100. So that.
Well, we don't know. We don't know what the worst case is by 2100. No, that's actually an important point.
Because if we keep going, that 65 meters is eventually going to be reality beyond our lifetimes.
Oh, that'll be I don't think that can happen in a few centuries. Okay, let's be clear. And I'm able to speak out. I don't work for a university, and I'm not a PhD. I really have a lot of freedom in how I frame this. But people listen to me because it makes sense. I mean, I've been vetted and so on. I think this century, in the worst case, we could get 5 meters. If we don't constrain the greenhouse gases, if we allow warming to just continue with abandon and burn all the fossil fuel we can, okay, we could get 5 or 10 meters this century. We don't know. We're watching the ice melt in Greenland and Antarctica. So let's be clear. The model I'm saying that the Dutch used, and I think it's a fair, you've got to decide where to put the stake in the ground. You know, it's like any risk. You know, is it a 1 in 1,000? Is it a 1 in 100 risk? Is it 1 in 1,000? Right? What's the risk of me surviving to tomorrow? It's pretty good, but it's not infinite, right? I mean, I could get killed this afternoon. And you price that into a policy. It might be 1 in a million chance, right? Think about it. That's what you do. So when you say, how bad could it be this century? You didn't say it that way, but let's just take your question and turn it around.
I was actually thinking longer time frame. I wasn't thinking about my life. I was talking about humanity.
We're going to get, it depends on how quickly we slow the warming, how quickly we cap that rate of greenhouse gases. We don't know. If we all went 100% solar and wind farm today, nuclear, okay, and hydro, all the non-fossil fuels, we don't know where it will stop because of the heat we've already put in the system. That's an honest statement. But let's say we capped it at 20 meters of sea level rise instead of 65. But we had 2 or 3 centuries to adapt. But the implications for that are so huge, not only for countries and national security and immigration and food supply and water supply, because it gets in the, you know, and. It's mind-boggling, right? Mm-hmm. You're probably sorry you came.
No, I wish my kids were here.
Okay. Sorry.
Yeah, when I was examining this about 15 years ago, I said the insurance industry had an issue because they work with actuarial models and a deductive way of thinking. They would probably have to work on more inductive ways of thinking with essentially more predictive models. I think you've just said even that inductive way of doing things has issues with it. Am I correct in that?
Yeah, it's limited because of this collapse potential. You know, and it's like a good metaphor is if you had a house and there was a dam upstream, you know, and it was an old dam and it was crumbling and there was water trickling through it. And somebody said, well, how long do you have before you got to move this town that's beneath the dam? And you can do all the measurements you want on the concrete. You're not going to know when it's going to collapse, right? You may get more and more water coming through. You can do lots of tests. Maybe get different results than for the last 100 years that dam's been there. That would be the inductive reason, saying, well, let's test the concrete. But there's a point at which that dam's going to collapse, and the truth is no engineer is going to tell you what day and how quickly. And that goes beyond the inductive reading, because we do those things typically based upon fine analysis and laboratory. We can test roof beams, or whatever it is. What's the word I'm thinking of?
Trusses?
Yeah, trusses, thank you. We can put them in a lab. I mean, we can wait till the snow collapses the roof and say how much snow is on the roof, or we can put them in a laboratory and break them, right? And now you know and get a range and so on. You can't do that with Antarctica.
Because right now with the insurance industry, by and large, it's still actuarial and
Sure.
That hasn't even moved into.
That's what the Geneva Association said. We come out of a culture of analyzing the past and predicting the future. It's a game change on this issue.
If you have time for one more question, one of the earlier slides showed the global heating much more severe in the north than in the south, and Antarctica looked to be almost insulated from the effect. Can you explain why that is, or
sure,
why that is?
Yeah. Okay. Because of ocean currents and atmospheric currents, and they're different. The Gulf Stream in the Atlantic, if you will, and the jet stream, ocean and atmospheric current. As the Arctic melts and does change, doesn't add to sea level, but it's going to have a different heat effect on those two issues differently, ocean atmospheric currents, right? But the Arctic is feeling the effects of this warming for several reasons, and I'm not an expert in this, but it's clearly happening. I think it's largely because you are able to melt sea ice in the Arctic around the North Pole and change things much more quickly than in Antarctica, which is 7 times bigger in solid land. So it can't possibly melt nearly as quickly, okay? And that map where they're measuring temperatures, and there were some blue spots, there was one off Greenland and there was one off Antarctica, there was some off Antarctica, you're right, it was very astute, that those are really reflecting the meltwater that's entering the ocean. That's why those areas appeared cooler, okay? But I think there's a phenomenon that I'm not the expert to answer this, of why the higher latitudes in the northern hemisphere are getting the brunt of the heat. Okay, that I think has to do with circulation patterns and also the tilt of the Earth. But I don't want to step past my expertise. Let's do some questions.
Yeah, running low on time here.
We'll
just get to one online question. I think most of the online questions are actually answered by the discussion here. But one participant asked how important it is to look at local sea level rise for planning as opposed to the global mean.
Yeah, absolutely, because of subsidence or uplift. And so, again, parts of Canada is going to probably have negative sea level rise, sea level falling for a while. But that's why we've got to be enlightened here, because even if, whether it be Alaska or northern British Columbia, the land's uplifting faster than sea level is rising, that's going to get overwhelmed as that Jakobshavn Glacier that we were standing on 2 weeks ago, and eventually the Pine Island glaciers in Antarctica flow into the sea. So this is where, just like you do in your own businesses, you know, with your underwriting and actuarial data and analysis, if we want to plan for a century or more and build in a safety margin, we need to do it with much greater detail than, obviously, I mean, I'm just doing the tip of the iceberg here, as it were.
Great, of course. Okay, I think we'll have to end it here. I know we have to keep going at 11:30.
All right, well, thank you.
Do you have any other last comments?
No, I don't know. I think we've covered it. I hope that this provokes thought and seize the opportunity, and whether you find other experts or invite me back. I mean, I love going around doing this stuff. I do it differently than most people. It's a pleasure to help the U.S. Coast Guard plan for it, but this is not a nationalistic thing. And in fact, the oceans really are global. And what's going to happen here, whether it's Hong Kong, whether it's Canada, whether it's Mexico, it's one ocean, but different cultures and different insurance practices. And obviously, insurance is really an important tool to get people to think about this and to begin to price the risk in different ways than we're able to do with normal catastrophic risk or life risk or all the other things that your industry has grown up doing. But that problem becomes an opportunity. It's just, it's sort of cliche, I know, but there is some truth in that, obviously, because it's whether it be the future of your company, the role that this institute plays as a think tank for the industry, we've got to wake up. I didn't have this figured out 20 years ago. I mean, this is pretty new information. I mean, I really stumbled through this, figuring out this so I could write a book, and I didn't really plan to get on the speaking circuit, but Hurricane Sandy happened a week later, and they somehow found out I'd written about it on page 121, somehow a year before it happened. I described a superstorm hitting Atlantic City in New York. So British Sky News TV in Britain said, this is the day after Sandy hit. They said, you described, I don't know, it's amazing, powers of the internet, they found that I'd written a book published a week before online that described that, didn't name it Sandy, of course, I couldn't have possibly known that. He said, how did you figure that out? I said, that's just dumb luck, I mean, that's just ridiculous. I didn't think it would happen, like, now. But, so one thing leads to another, and this, our meeting in Calgary is an example. So, hope you do something with it.
Thank you, John.
Thank you. Thanks a lot.
Thank you very much.
And you got the email address. If you do that, you'll get a downlink and some other stuff, and you'll know how to contact me. Okay, great.
Thank you.